I'm Ori Nizan. I'm currently doing a PhD at the Technion. And my main field of study is domain transfer, image domain transfer mainly. And this work was part of this research. Okay, thank you, Peter, for organizing this talk. And maybe I'll just share the screen.
Mm-hmm. You should be able to let me know if not. Yeah, you should be able to.
I think, yeah. Okay, so you can see the animations, right?
It's not moving. It is moving, yeah.
All right, so maybe there is a little bit delay. Okay.
Mm-hmm.
Okay, so our work deals with image-to-image translation between unpaired domains. Here you can see three typical applications: glasses removal, male to female, and anima to selfie. We named it Breaking the Cycle, Calling All You Need. This work was done in a collaboration with Eletal from the Technion. Mapping between different domains is in line with the human ability to find similarities between features in distinctive yet associated classes. So it is not surprising that image-to-image translation has gained a lot of attention in recent years. The problem we tackle is unpaired image-to-image translation, where we would like to transfer an image from one domain to the other when matching pairs does not exist. For example, when translating an image of a man to a woman, we do not have a woman image that matches that man. This differs from translating gray image into color one, where we can train with matching pairs. Furthermore, we would like the output to be multimodal, which means we would like to produce multiple output for the same input. Previous method might suffer from some drawbacks. For example, the preservation of source domain features, as can be seen here. We can see that when converting a domain with glasses to one without glasses, glasses are still visible in the resulting image. Second, sometimes those methods are unsuccessful for tasks with large shape changes, such as in the case of Selfie-to-anime. Another problem is that they usually need to create a network for the backward translation, when this could be harder to train, and for some application, it's unnecessary. We propose a novel approach termed Council-GAN, which handles these challenges. The key idea is to rely on collegiality between GANs. Specifically, instead of using a single pair of generator, discriminator, export, it utilizes a collective opinion of a group of pairs and leverages the variation between the result of the generators. This leads to more stable and diverse domain transfer. We demonstrate the benefit of our approach for several applications, including glasses removal, face-to-anime, and male-to-female translation. In all cases, we achieved a state-of-the-art result. Hence, our work makes the following contribution. First, we introduced a novel model for unsupervised image-to-image translation, whose key idea is a collaboration between multiple generators. And second, our council manages to achieve state-of-the-art result in a variety of challenging applications. Okay, so since the introduction of GAN, Generative Adversarial Network, it has been demonstrated to achieve eye-pleasing results in numerous applications. In this framework, a generator is trained to fool a discriminator, whereas the latter attempts to distinguish between the generated sample and real sample. A variety of modifications have been proposed in recent years in an attempt to improve GAN results. The classical GAN usually uses a Gaussian noise as input. In our problem, in image-to-image translation, the input to the generator is an image, and the aim is to learn a mapping from source domain images to target domain. The early approach adopts a supervised framework in which the model learns paired example. For instance, using a conditional GAN to model the mapping function. A quick explanation on conditional GAN. Conditional GAN changes the input to the discriminator, and instead of only getting the generator output, it gets also its input. Both the input and output are coupled together and are sent to the discriminator. This way, if the generator produces an image that does not correspond to its input, the discriminator can easily identify it as fake, as in real examples, they always match. Recently, numerous methods have been proposed which use unpaired example for the learning task and produce highly impressive results. This approach is vital to applications for which pair data is unavailable or difficult to gain. Our model belongs to this class of GAN that do not require pair training data. The main problem is the power of the generator. The generator can produce any image given any input image. This is why we need to add a constraint that connects the input to the output, which will force the generator to produce images that are similar to the given input. A major concern in the unsupervised approach is the type of properties of the source domain that should be preserved. For example, some use pixel values, pixel gradient, pairwise or pairwise sample distance, and recently cycle consistency. The latter enforce a constraint that translating an input image to the target domain and back should obtain the original image. Our model avoids these cycles altogether. This has the benefit of bypassing unnecessary constraint on the generated output. Most existing methods lack diversity in the result. To address this problem, some methods propose to produce multiple outputs for the same given image. Our methods enable image translation with diverse output. However, it does so in a manner which all GANs in the Council acknowledge to some degree each other's results. We are not the first to propose the use of multiple GANs. However, previous approaches differs from ours in both their architecture and in their goals. For instance, some of previous architectures consist of multiple discriminators and a single generator. Conversely, some propose to have a key discriminator that can evaluate the generator result and improve them. We propose a novel architecture to realize the concept of a council. Furthermore, the goal of the other approaches is either to push each other apart and create diverse solutions, or to improve the result. Our council attempts to find commonalities between the source domain and the target domain. This is done by requiring the council members to agree on each other's results. And they in fact learn to focus on the common traits of the domains. A note on ensemble methods. These methods use multiple learning algorithms trained individually, whose predictions are combined. They seek to promote diversity among the models. The models are not pushed together to be similar, but rather they benefit from being different. Conversely, we require the council to learn together and converge to agreeable solutions. So for the model, our model consists of a set termed the council, whose members influence each other's result. Each member of the council has one generator and couple of discriminators. The generators need not converge to a specific output. Instead, each produces its own result, jointly generating a diverse set of results. During training, they take into account the images produced by the other generators. Intuitively, the mutual influence enforces the generators to focus on joint traits of the images in the source domain, which could be matched to those in the target domain. For instance, to transform a male into a female, the generator focuses on the structure of the face on which they can all agree upon. Therefore, this feature will be preserved. Furthermore, our model avoids cycle consistency constraint. This means that there is no need to go in both directions between the source domain and the target domain. And as a result, there is no need to leave traces of the generated image or limit the amount of change. Here we can see that we can remove large objects such as the sunglasses from the input without leaving any traces.
Oli, can I stop you for a second? I had already two questions I wanted to ask.
Okay, yeah, sure.
So you mentioned that your method is not an ensemble method.
Yeah.
Is it something that you're going to be explaining further on, or maybe I missed the idea?
The ensemble method, usually you take a couple of, like in classification, you train each one individually, and the combined result is like better than each individual one. But you don't try to make each one of the ensemble members to be the same. Right? Okay. If they are the same, it's actually worse a little bit.
Yeah.
Yeah. So this is the main difference. Ensemble is, yeah. don't try to converge together. It's each one individually, and then the combine is like average or something more sophisticated.
Mm-hmm.
Yeah.
And this also, and this connects to my second question. You mentioned it's cyclically consistent. I think you mentioned this phrase in the previous slide.
Yeah.
So I think it relates, but I couldn't understand totally what this means.
Yeah, it's not exact. Cycle consistency is what's the main method to constrain the input to be related to the output. Mm-hmm. The idea is that if you can transform an input to the output, and then you have another generator that transforms back. Mm-hmm. If you constrain that the start of the cycle and the end of the cycle are the same, it's actually a good constraint that in the first translation is actually a good one. Because if it's not, it can't go back to the same image. Mm-hmm. This is the main idea.
And I think two slides forward. One more, I think, and a bit more, maybe even. Yeah, this one, previous. The one where you have 3 photos of a woman on the right side, I think 2 back. Where you
again?
One more back.
Oh. This.
No. Yeah, this one.
This.
No. After this.
Maybe it's in delay. Yeah.
Yeah, it's in delay. So here, you mentioned that the 3 generators, they generate a feature set which is consistent among the 3 generators, right? For example, a female's characteristic face, if I understood what you said correct.
I don't exactly know, but this slide, like each color. Okay, yeah. Each color is like its own, do its own thing. They are not connected. They have the same architecture, but they are not connected. The weights are independent. Mm-hmm. But the constraint is that they need to produce images that are similar to one another. And we will, in the next couple of slides, we'll explain how exactly this constraint actually works. Yeah.
And this is the part that separates your method from an ensemble method.
Yeah.
This constraint. Okay.
Yeah, exactly.
Perfect. Thank you.
Just sure. So what is the difference between the members? It's a different architecture everywhere.
Again, I didn't hear.
What is the difference between members? Is it different architecture?
The members are identical except their initialization. Each have different weights. And they are, they don't pass information during training, except for the loss at the end.
And when you initialize, is it just from some from some type of distribution? What is it?
It's the normal ensemble from M-Unit, famous architecture. It's not anything unique. Like Xavier, I believe. Yeah.
Okay.
Cool.
Yeah. So I think we were here. Okay, so each member of the council consists of a triplet of 1 generator and 2 discriminators. The task of the first discriminator is to distinguish between the generator's output and real examples from the target domain, as done in the classical GAN. This generator informs that the generated image should belong to the output domain. Okay. The second discriminator distinguishes between its own generator output and those generated by other generators in the council. The generator that tries to fool the discriminator will try to produce images that are similar to the other generators in the council. Right? This is how the council loss works. In order to produce such images across the entire domain, they need to coordinate and agree on common output rates. Because the only thing in common between all of them is their input, they should reach an agreement based on it. In other words, there are many ways to produce a random output, but only a few that are related to the input. And this small space of agreeable images will minimize the council loss. This is why the output should share common traits with the input. Sorry, just a second. One more thing to notice is that the discriminator doesn't only get the generator output, but also its input. This is done in similar way to the conditional GAN we saw earlier. We do this because we don't want the generators to produce similar output in general, but similar output for similar input. To implement our model, we define a loss that has 3 parts. GAN loss, which is what makes the generator's output belong to the output domain. Council loss, which is what makes the generators reach an agreement. And we added the focus loss. This loss helps the generator to change just a small part of the image.
Excuse me, can you repeat it? What is the focus loss?
Focus loss, I will talk about it in a couple of slides. I didn't mention it before. Yeah, it's a new thing. In a couple of slides, it will be explained. But about the council loss, each iteration, the council discriminator gets as input and input-output pairs from all the generators in the council. And instead of telling the difference between real and fake images, it tells the difference between images from its own generator and other generators in the council. To enable multimodal output, we first encode the input image. This encoding should contain the common information between the domains, which we would like to preserve, like head pose, for example. In addition, we added a random entropy vector that should contain the rest of the information that is not shared between the domains and should be added, like facial hair when translating from female to male. What is added to our equation is the encoder and the random entropy vector. In addition, we use that entropy vector to help the council converge. When training the council discriminator, the generator that belongs to the current discriminator produce an image with all the entropy vector. But when the other generators produce their images, they do it with the subspace of the entropy vector. In practice, we multiply the entropy vector with alpha, which is a number between 0 and 1. This means we gradually shrink the space that the generator are producing. For clarification, the current generator doesn't try to produce images that are similar to the other generators, but a subspace of them. And the other council members do so as well. This has the effect of gradually shrinking the space that they agree upon. The space will continue shrinking until a balance will be reached between small conditional subspaces possible and spanning the entire output domain. This is our final loss. The shrinking of the space will be done with the addition of alpha in the equation. A bigger alpha will result in slower convergence, but will typically have more diverse and multimodal output. We set alpha at 0.7 for most of our experiments.
Oli, can we pause a bit on that slide you showed?
Yeah.
The equation is it's a bit big and it's interesting to understand all parts.
Mm-hmm. Yeah.
So there's DI and DJ, I think I saw before. Now I see both only DI. GI and GJ. Yeah. And this is the same discriminator, discriminating from different generators, right?
Exactly. If you go back to this slide.
Yeah.
Maybe I'll just jump like this. Wait just a second. Yeah. So each one of them, have its own. Sorry for this, but each one of them has its own council discriminator. The council discriminator of this guy gets this one as a fake, and the real and the others as a real. Yeah.
He gets what is fake? The generated.
This one gets. It needs to classify its own generator as fake and the others as real. This is why this generator will try to fool this discriminator and produce images that are similar to this guy and this guy.
Ah, so yeah. Oh, okay.
And the others do it, yeah, they are symmetric. This guy tried to produce like this one and this one, yeah, and this one tried to these two.
And the D1 without that that small hat on top, this is what?
This is a normal discriminator. Its job is to make the output domain, the generated image to belong to the output domain.
Ah.
And that has the same architecture as all DIs?
All the Ds, like the D hat, have the same architecture. The D, each block has the same architecture as each block.
Yeah, but the D1 head has the same architecture as D1.
They are not exactly the same because this one is a conditional discriminator. It's got also the input. So it's a bit bigger, but they're essentially very similar. Just the input is 6 dimension. Yeah, that's instead of 3. So it's like the concatenation of the input and the output.
Is the regular discriminator has shared weights? Yes, these ones.
No, none of them has shared weights.
Okay.
Like between the, this and this are not shared. Yeah.
Okay.
No shared weights anywhere.
Thanks.
Can we look again at the equation, that the big one?
Yeah, sure.
There were so many characters there. It takes a while to understand them all together.
Yeah, sure.
This is good here. Yeah, this is very good.
If
so
you like, it is. I try to do it in parts. Maybe I'll go back a bit. Like here, this one is the more simplified version. Like here, GI is actually consists of the encoder and the decoder. So this is what's the difference between the equation. So yeah, this discriminator tries to distinguish between its own and others, J.
Yes.
This part is clear. Yeah.
Yeah, and it also gets that real image from the domain, the X, small x. Is this right?
Yeah, exactly. This is why it's conditional. Yeah. Yeah. This is because we don't want them to produce the general same images, but the same images for the same input. Yeah, so it's conditional on the input. Yeah.
So that's right.
If one generator produce, like for example, blonde, and the other produce black, the generator, condition on the input. So yeah. So if I confuse. Yeah.
You mentioned that when I is not equal to J, that discriminator with the hat, it takes the generated image as a real image, right? That's the idea. It addresses the generated image, the fake image, as a real image because it's not from the same member group.
Yeah, exactly. It's analogy to the normal discriminator, which has just real and fake.
And why does it need to get the real images from the domain also on the right part? On the left part, I can understand, but on the right part, why?
They are both, because it's the same discriminator, its input is the same every time, whether it's from its generator or other generators. So it always discouples. Yeah.
Okay, I understand. Thank you.
Yeah, sure. So just a second. Maybe here. So this equation is just the previous one where the generator is open up and the encoder is over here. This is why we added the entropy vector, what I explained earlier. This is why I needed to open up this equation. Yeah, because the alpha shrinks for the other generators. The generator its own generator produces the entire entropy vector and others with the subspace. So, if we will try to explain it again, like here. Yeah. So the red D gets a generator that outputs the entire entropy, but the blue and the green produce a subspace, right? And with an alpha that is number between 0 and 1.
Why is it interesting? Why do we need to put that entropy there?
You don't want them, like they can agree on the entire domain. You want it to be as small as possible, essentially. They can agree on the same small space of the, like a blonde. You don't want like they can agree on everything. You want it as small as possible, like from a blonde male to a blonde female.
Ah, so you want to make that random noise a bit less so the domain keeps stable. Mm.
Yeah, so more stable, yeah. Instead of, they can take blonde male and make all the color hair females.
And we don't put
it to be small as possible. Like they need to agree as small as possible.
And we don't put this in the same generator from the same member group because we want to put that extra noise and still have it generate images on the same domain.
Shrinking. Yeah, it's shrinking. Yeah.
Okay.
In the beginning, it's more big, and then it starts shrinking. This is the Okay. So now for the focus loss. In some application, in order to let the generator focus on a small part of the image instead of changing all of it, we added a mask as a force channel and a focus loss is defined on it. The idea is to let the generator produce not only an image, but also an associated focus map, which essentially segments the learned object in the domain from the background. We added the force channel to the generator's output, and now instead of producing 3-channel output, which are the RGB, it produces 4. And the force is considered a mask, where 1 represents a pixel that is taken from the generator, and 0 represents a pixel from the input. And on this mask, we define the focus loss. The focus loss has 2 parts. The first term attempts to minimize the size of the focus mask and make it focus solely on the object. The second term is in charge of segmentation. The image segmenting the image into background and foreground, essentially make the mask binary. The delta value changes based on the application. For example, in the glasses removal application, it should be big because the relative ratio of the image that need to be changed is small. In the final loss, lambda 1 controls the importance of looking more real or more in line with the other generators. High values will result in more similar images, whereas low values will require less agreement and result in higher diversity between the generated images. We need to be careful from setting lambda 1 to be too big because it can result in council collapse, which means the council will coordinate on a trivial solution like ray image and will ignore the requirement that the image should also belong to the output domain. One solution to mitigate this problem is to not start the training with the council and focus losses, rather just the GAN loss, and after a certain number of iterations, start using them as well. Lambda 2 controls the size of the image to be changed. In Selfie-to-anime, for example, it should be set to 0 as all the image need to be changed. Here we can see the importance of the various losses. If the focus loss is used, the phase of the input and the output are unrelated, but the quality of the images is good and the background largely does not change. Using only council loss, the phase of the input and the output are nicely related, but the background might also change. Our loss, which combine the above losses, produce the best result. We note this idea of adding the force channel, which makes the generator focus on the proper area of the image, can be used in other GAN architecture and is not limited to our proposed council model.
Just a moment, can I ask a question?
Yeah.
So, in fact, you don't have one generator, you have many generators.
Yes.
You have many members. So when you show results, so what actually you show? You show one?
Here is the council of 4 members, and from each member a random output.
So in fact, you want just show that when you add all these losses, when all the generators converge to the same solution, if I understand correctly.
They converge not to exactly the same solution, but like the mail that connect. Yeah, you can see similar features. Yeah, to the input. They're not converging to pixel-wise difference from each other. This is why we added the counselors. It's more like general, not pixel values. Otherwise, the generated image will be blurry or something.
Mm-hmm.
So actually, Oro, you mentioned something very interesting before when you did the testing, that you just left. First, you did a couple of iterations of training only with the regular GAN loss. And once this stabilized a bit, then you added the other. This is a cool trick. I think it's the first time I'm hearing of something like this, but it makes sense. Yeah, it's a very cool move.
Okay.
I wanted to ask you something also. If you can go back to the first slide about the focus loss where you had the mask definition.
Yeah, sure. This part.
I maybe even there was one before you also mentioned mask, I feel.
This one?
Yes. Maybe I missed it when you said it. Is the mask used as input during training, or how is it?
The mask is created during training. Like usually here the generator gets an input, an image, right?
Yeah.
It has 3 channels, RGB, and usually it produces an output that is also 3 channels, which are also RGB. You can just add parameter that you have a 4th channel. And you treat it as, I treat it like a mask. So after that, there is additional step where you have the 3 channels that the regular generator produce, the 4th channel, and then you take this 4th channel and you multiply it with the generator output, and plus the input and one minus the mask. And the other one,
so actually, when the discriminator for the focus, there is a discriminator for this mask, by the way. Maybe I must.
There is no discriminator for this mask, but this mask has a loss on it.
So you combine.
It should be as small as possible.
And how is the loss calculated? Is it like the difference between the different generators, and then you try to minimize the difference?
It doesn't look at all at different generators. The mask by itself has a loss on it. So each one of them has its own loss, essentially. This is the loss.
But how can you, what do you compare the mask to compare the loss?
Nothing. The mask just need to be as small as possible. Small as possible. It can't be 0 because the generator then can change the image. If everything is 0, it's just the input. You're left with just an input. So it has to be a little bit bigger so it can change what the minimum amount will change just the glasses. It's an additional requirement. It makes the better outputs.
So I'm missing something. Why doesn't it converge to 0? Where is it? What keeps it higher than 0?
Yeah, it still need to produce an image that belongs to the output domain. If it just be 0, it will be the input domain, and the discriminator will easily see it. Yeah, it can. It's not from the output domain, so it can not good.
So the 2 other discriminators, the GAN discriminator and the council discriminator, they balance the mask, so it is not 0.
Yeah, exactly. Right? In a way, yeah.
Okay.
Can I just ask a question about this? The mask that's generated, here you have an example where it's generating a mask that outlines the glasses really nicely. Does this only happen when your 2 domains are glasses and not glasses, or is this something that happens for other domains? One of the generators decides to focus on glasses.
This application specifically benefits a lot from the masks, but others also tend to benefit it. But it's not like here. It's clear.
The difference between the 2 domains.
Excuse me, I can't.
Oh, sorry. The masks that are generated, they tend to reflect the differences between the 2 domains. Nice.
Yeah, exactly. This is it usually over here it's really reflective
So it ends up being a
on
kind of
this
segmentation.
application. Yeah, exactly. Unsupervised segment.
Yeah, that's very nice. Thanks.
Yeah, it's super cool. I think we're going to be marking the cool stuff you did already during the lecture. Yeah.
So, okay, so where were we? I think we were here. Okay, some methods we compare against were multimodal. All of them use cycle constraints. Some of them are multimodal, and the other produce a single result. Yeah, okay, so for the data set, we evaluate the performance of our method on the following dataset. First is Celeb A. This dataset contains about 200,000 face images of celebrities, each annotated with 40 binary attributes. We focus on two attributes, the gender attribute, with and without glasses attribute. And with and without glasses attribute. The second dataset is Selfie-to-anime. Its size is 3,500 selfie images and 3,500 anime images. The size of the test set is 100 selfie images and 100 anime images. In this dataset, the number of images is small. This is why we augmented the data by using color jittering, random grayscale, and random rotation. The random rotation have a big improvement when used on this dataset. On the last 100,000 iteration, we train only on the original data without augmentation. Okay, a little bit about the training details. All models were trained using Adam and with some data augmentation. An important detail about the council discriminator is because it has harder time than the generator due to the fact that it has to keep track of multiple generators. For each iteration of the generator, we train the council discriminator a number of times that is equal to the size of the council, which means for a council size of 4, the council discriminator will be trained 4 times for each generator's update. Because we have 2 discriminators with 2 different objectives, so in order to keep the loss in the same range, we normalize them using a window of the last 100 iterations. And to prevent the council from collapsing and agree on a trivial solution, as we discussed earlier, we didn't start the training with the council and focus losses. These were added after about 10,000 iterations. We use council size of 4 for most of the experiment. The smaller the council size, the faster the convergent, but it also tends to converge on output that is less related to the input. On the other end, if the council size is too big, the council will not converge at all. And about the computational cost, the training takes about twice the time compared to CycleGAN when the council member runs sequentially on the same GPU. The longer time is due to 1, having multiple council members, 2, a longer iteration of the council discriminator, and 3, twice as many iterations needed to reach an agreement. It only takes twice as long since we avoid learning the reverse side of the translation. Yeah.
Oli, can you mention
yeah.
Training time? What was it?
About twice as long as the CycleGAN.
Effectively, how long was it?
I believe it took us 3 days for most of the 3 days to a week on most of these applications.
On all the
It
data
depends on
sets
the
about
size of the image, yeah, but yeah, comparable.
Uh-huh. And what hardware did you use?
We have a Quadro. This is the best one.
Quadro?
Quadro P6000.
What is this? Is
Quadro
it like a
P6000.
local server?
This and yeah, we also have the 280, the 2080 Titan.
Ah, the Titan. Okay. And
Yeah,
and with the Titan, for example, it was 3 days.
2 of them. What again?
You had 2 GPUs on the same machine?
In the beginning, no, not on the same machine. Those are different machines.
And the training was running on both simultaneously, or how?
They are ran different experiments.
Ah, okay. So for example,
Yeah.
with the Titan,
The quadrupisa 6,000. Yeah.
can you repeat that? It broke off for a
Sorry.
second.
The P6000 is have more memory. So maybe the P6000 have more memory. So if you want to train with the 256 images, 256 on 256, you have to use it. But for the left side, you can train on the smaller CPU.
Okay. And if you can come back a bit, you mentioned something about you did a window normalization between the different discriminators, taking a couple of epochs of training back in order to account for something. But if you can, I think when you talked about normalized two discriminator losses, and you mentioned something about a window normalization, if you could repeat it.
Yeah, over here, because we have two discriminators, and the loss of a discriminator is not exactly matched to the quality of the generated image, but the discriminator and generator produce, they are comparing one to another, but if the discriminator loss is smaller, it's not essentially mean the image quality is better. And we want to normalize like the power of each of these losses, like the council and the GAN loss, to be comparable to one another. So the generator won't just use just one of them, essentially. So we normalize them, with the last 100 iteration of each of them.
It's a bit hard to visualize, to imagine
maybe
what it means.
I didn't think that this part is that important, so
no worries. Is it written in the paper in a way that is clear, or somewhere else where we can read after?
Okay. Yeah, next time
Hello, you're breaking off. You broke off.
It's in the, can you hear me?
Now I think we can.
Yeah, okay. Yeah, hopefully this problem won't continue.
So I think we couldn't hear your answer. I asked if there will be any reference where we could read about this.
Yeah, I believe it's in the supplementary. If you look on the page. Yeah.
Yeah. So the supplementary for anybody who's listening to the recording, if you look at the paper or on the slides, at the paper, right?
In the paper, yeah. On the project page, you can find all the supplementary. If it doesn't on the same PDF.
Okay. Yeah. Thank you.
Yeah, sure. Okay. Now.
And the whole council of GANs was trained in the same two-step process that you usually use for GANs, or was each one? They all had the same batch at the same time. Is that right?
Yeah, exactly. It's very analogy to the regular GAN.
Okay.
Yeah.
Okay.
Okay, just a second. Okay, you can accelerate the computation if you try to use a council of smaller size. It can work. We didn't have enough time to train all the different possibilities. You can also try to share some of the weights of the generators, like to have the shared encoder, for example. But we didn't experiment this really long, but it also can benefit the computational time.
This reminds me of another question I had.
So about
you mentioned that if you go with too many council members, then there is no convergence. I think that's what you said, right?
So how did you confused? Yeah.
Yeah. So how did you come up with 4? Why not 2, 3, or 5?
Basically, 4 was a number that works, but if you think about it, like one generator try to be like 3 others. So 2 are good and maybe 1 is bad. So the average direction should be good. This was the high level. If I try to move me to be the same as the 3 others, hopefully the average will be okay.
Yeah. Also cool trick. Nice.
Yeah, thanks.
So you pre-assume that there will be convergence to a good spot,
Yeah,
but you say it won't be an optimal convergence. Maybe some won't converge, but then you say if
yeah,
on
exactly.
average there is
And you
convergence to
don't
a good
want it.
spot.
Yeah, exactly. You don't want it to just converge on some random thing or yeah.
Mm-hmm. Cool.
Yeah, thank you. Just a second. Okay. About the, someone asked a question.
Yeah. So the dimensionality of the weights is so high, and that just any for initializations may be very far away, and if you don't use all these Council-GANs, they can converge to any other place, to any other image. So are you so sure that
Yeah,
it's
exactly.
not? So doesn't it depend on the initialization? So if, let's say, initialization is very far away from the start, then it will never converge. So you should have some. Are you sure that
Yeah.
always will
Maybe the entropy vector, it's like in the beginning, it's more large, you can say, you can think about it like this, and little by little it's converged. So yeah, if they are maybe too far apart really, then nothing will help you. But if they are similar in area, yeah, because the random entropy vector is still spread across in the beginning, and then slowly shrinks. So hopefully that's answer. Yeah. Okay. Okay, a little bit about the quantitative analysis. Coming up with a measure for quality of the resulting image is a hard problem based on the subjective value of what can be considered a good image. The first measure that was introduced was with human evaluation. Inception score uses inception network that was trained on ImageNet. It compares the conditional label distribution with the marginal label distribution. Here, X is the generated image and Y is the result of the inception network calculated on the tested generated images. The higher the inception score, the better the result, which means it tries to maximize the KL divergence between the label distribution given an image and the marginal label distribution. This means we would like to push these two distributions as far apart as possible. This can be done when the label distribution given an image have low entropy, which means the inception network output a sparse label for each generated image. Intuitively, it means the inception network detects an object in the image and not give a uniform random across all objects. And the second thing to maximize this scale divergence is that the marginal should have high entropy, which means the combined generated images should produce diverse set of labels. You can intuitively try to understand what this inception score try to achieve when you look at this diagram and this equation. This equation is essentially the KL divergence, and Py of X, X is the generated image, and Y is the label of inception network that was input that generated image. Essentially, it should be like one hot vector. Yeah, and P of Y is the average of all of them. Okay, so if you would like to these two to be as far apart as possible, you would like those to be as close as possible to one hot vector. And this one, which is made up of those, is the average of those, to be as close as possible to a uniform distribution. Right? This gives the best inception score. So we want to have a meaningful classification, essentially. And the classification should be uniform across all the objects. Essentially.
Maybe I missed something about this. Or maybe if we can explain this, maybe again. How come the classification is different for each member of the ensemble if they all generate an image which
this is the general inception score. It's not connected to ensemble or anything.
Okay.
Just you have a group of generated images,
Okay.
right? And this is how you compare if they are good or not. This is the famous inception score. Yeah.
Okay.
The next measurement is the FID, the feature inception distance. This is an improvement on the inception score, and the difference from inception score is that it compares the statistic between the generated image and real images. Inception score works only on the generated images. The feature distance is also known as the Wasserstein-2 distance. FID uses the last activation layer, which produces 2048 features for each image. To calculate the FID, we sample a large number of generated images and real images, each produce a vector of size 2048, and use the formula to calculate the FID. Mu R and mu G are the mean of these vectors for each group. This means they have a size of 2048 elements. The sigmas are the covariance matrices. A recent improvement on FID is the KID, the kernel inception distance, which is based on MMD, maximum mean discrepancy, which is a distance between feature means. Like FID, it uses the inception activation. However, KID have the advantage that it also compares the skewness of the different distribution, as well as the mean and variance. And another important benefit of KID is that it has unbiased estimator, because FID changes its expected value based on what the number of samples used to calculate it. I have a little graph here, maybe I can show it. Yeah. So here is a comparison of the same distribution against itself used with FID, like celeb A against celeb A, the same distribution. And you can see that FID changes its expected value based on the number of samples used to calculate it. This isn't a good idea because if you want to know which algorithm is better, it shouldn't have a strong dependence on the number of samples used to calculate it. So this is this. Okay, so the first task we tackle is male to female translation. The problem is that given an image of a male face, the goal is to generate female which resemble the male. Three features make this translation task challenging. There is no predefined correspondence in real data of the domains. The relationship is many to many. As many female mappings are possible, and capturing realistic variation in generated faces requires transformation that go beyond simple color and texture changes, and as humans, we are more sensitive to artifacts in faces. Here we compare our result generated by a council of 4 members. Note that each of the council members may generate multiple results depending on the random entropy vector. We observe that our generated females are more feminine. The beard completely disappears, while still preserving the main features of the source male face. This can be attributed to the fact that we do not use cycle to go from male to a female and back, and thus we do not need to preserve any masculine features. This table summarizes our quantitative result, where our results are randomly chosen from those generated by different members of the council. Our results outperform those of other methods in both evaluation metrics. This table, the smaller the better in this table. The second task we tackle is the interesting selfie-to-anime translation. Given an image of a human face, the goal is to generate an appealing anima which resembles the human. This is a challenging task as not only the style differs, but also the geometric structure of the input and the output greatly varies. This might lead to mismatching of the structure, which would lead to distortion and visual artifacts. This difficulty is added to the 3-channel GANs mentioned in the previous application. The lack of predefined correspondence of the domains, the many-to-many relationship, and going beyond color and texture. Here we again see our result using a council of 4 members. our generated anima images are quite often better resemble the input in terms of expression and face structure than those of other methods. This can be explained by the fact that it is easier for the council member to agree on features that exist in the input.
Oli,
Yeah.
one question. The examples, are they cherry-picked or random?
Here is from the part from the paper, so it's more cherry-picked.
Mm-hmm.
Yeah. Mm-hmm. But we have a lot of examples in the supplementary if you just want to look at many examples. Yeah. Okay, here is the quantitative result. It can be seen that our result outperform or are competitive with those of other methods. The next task is glasses removal. Given an image of a person with glasses, the goal is to generate an image of the same person but with the glasses removed. While in the previous application, the whole image changes, here the challenge is to modify only a certain part of the face and leave the rest of the image untouched. Here we compare our result to those of fixed point, which shows result for these applications as well. Our generated images leave considerably less traces and remove the glasses. Again, this can be attributed to the lack of cycle constraints. Here we provide quantitative results for this application as well. Our council manages to outperform other methods and address the challenge of removing large objects. A limitation. We notice a limitation of our method that is demonstrated here. When removing the glasses, the face might also become more feminine. You can see the lipstick that was added to Harry Potter here. This can be attributed to the imbalance inherent in the dataset. Specifically, the ratio of male to female with glasses is 0.8, whereas the ratio of male to female without glasses is only 0.4, meaning that in the source glasses domain, there are more male with glasses than female with glasses, and in the target domain, it's the opposite. There are more female than male. The result of this imbalance is that removing glasses also means becoming more feminine, for this domain at least. This problem can be solved by providing a dataset with an equal number of males and females with and without glasses. You can say that this problem occurs in lots of domain transfer tasks. For example, also here, when trying to transfer a man to a woman, glasses also have a tendency to disappear. It is more noticeable in our method because we don't have a cycle constraint, which is in essence have a stronger pixel-wise loss. Handling feature imbalance is an interesting direction for future work.
Question?
Yeah.
Here in the last slide, if you reduce the alpha, it didn't improve the results? Like
the alpha doesn't, because the other domain actually have more females. The discriminator just try to reduce the distribution of the output domain. It doesn't really know what is what. So if it have a lot of female and here and on this side there are a lot of male, so male should become more feminine because otherwise the discriminator won't be happy.
Yeah.
Yeah, exactly. So yeah, so in essence, this is the problem definition. Yeah. Okay. We introduce the concept of Council-GAN, a novel approach to perform image-to-image translation between unpaired domain. The key idea is to replace the widely used cycle consistency constraint by leveraging collaboration between GANs, with the objective of reaching a consensus on their output. This method has a couple of benefits. One, it doesn't leave artifacts. Two, remove large objects from the image while keeping the rest of the image unchanged. And three, deals with large structural changes between the domains. You can find our work on GitHub. And now, if you would like a little demonstration, if you have a Telegram installed, you can search for Council-GAN bot and send it an image, and it will send you back its female translation. I can maybe show you.
Show us, yes, please.
Yeah, of course. Here, this is the Telegram. You can also do it on your phone. And if you,
This part I'm already predicting. This part will be the part which everybody watches on YouTube.
Sure. If you can find just any face you want, yeah, and take a screenshot, yeah, and you can do send. And if everything works, it should come back with the results. It's not 100%. It's random entropy vector doesn't always.
This is amazing.
Yeah, but you can also just to use random images, and you can also do it with the font. By the way, you only see your own result. Yeah, we can see your if you would like to share. Yeah.
Yeah, or if you can show us the link, if you can. I don't think there is a link on the slide which we can press.
I'll try to add the link, but it's just a Council-GAN in Telegram. It's the first.
I'm gonna send it on the chat. Because this is a good time to send this to people while we're asking questions, and everybody who's tried can demonstrate what they found. Telegram.
Yeah. So yeah, it doesn't always produce the best result, but it sometimes works. Yeah.
So I sent this on the group chat. I sent the Council-GAN Git project. You have a link to Telegram. Anybody who's here, feel free to show us the demonstration. It's now time for questions.
Because it was trained on Celeb A, the faces are better. It works better if they are aligned. Yeah. So if you just do from this angle, it maybe won't work as well.
By the way, front angle?
What? Like
a front angle, you mean?
Like straightforward. Like straightforward.
Mm-hmm.
It runs it doesn't matter how far away. Because it have so you can take even a big picture, but and it should,
you are cut off, or we can't hear.
Change one.
Can you repeat? We couldn't hear.
Sorry. I said it also works on multiple faces in the same image. If you have this kind of images, and
that's cool.
If you go to if you want to
again cut off.
Anima.
Again cut off.
The anima part, you can go to the GitHub. So that's a problem.
Yeah, again cut off.
Can you hear me?
Yes, now we can.
Okay, so hopefully, if you want to try the anima translation, you can go to the GitHub page, and in the bottom there is a link to a Colab notebook, and over here there is the upload images here. You need to run it, and you can just choose the images from folder in your computer.
Mm-hmm.
It will work. But I need to run everything again, so maybe
No, we don't have to do it now.
Yeah.
I hope somebody here in the group will do a run by himself and show us. Sometimes people do, and it's fun.
Yeah. Maybe it will take but it should produce the result in the middle, and also in the folder here you can see the results.
I'm gonna send it also on the Discord channel later on for people to play with. Is this exactly the type of things that people in the group like to run?
Yeah. Just need to download it from the beginning, so it will take a bit of time. If there are any questions,
I have questions, but please, if anybody else has, feel free to go ahead, and I'll ask mine last.
Yeah, I have a question, I think. So I want to understand it not from mathematical point of view, but from like reasonable point of view. So for me, cyclic GAN is very intuitive, because you really want, it's a kind of thing that I know exactly what should be from what I studied, and it really imposes this output image to be similar to the input image. So here I see, I understand very well that you just shrink the, in fact, it's my interpretation. In a way, all these new losses and this D-head architecture, it changes the shape of.
I'm sorry, you just cut off. I can't.
Okay, so
the last part I can't hear.
Okay, do you hear me now? Do you hear me?
I think Ori is disconnected.
Okay.
Yes, now.
I'm gonna turn my video off.
I
Maybe
have
this will
a
help.
little bit of a problem. Yeah, over here. I can hear you, but
So maybe I will write it. It will.
I try to understand. Wait, you can hear me now?
I will write it in chat.
Yeah, Ori Ina will write for us on the chat so we could see the text. This question yeah. The question will also be posted as references.
Okay.
I think it was something to do with if you, well, let's let her ask. So I don't assume.
Yeah, I can't see.
I will tell you when it's up. I'm looking at the chat. No worries.
Okay.
I will let you know. In the meantime, if I can ask while she's writing, the mask part still, it's interesting. I don't feel I completely got it. So after a mask is generated, how is it used to generate images in the direct, in the like required image? What's the word?
The last image, the final output. This is what you mean?
Yeah, here. How is it how is this final output using the mask?
Yeah. Okay. So the mask is just one hot, like zeros or ones each pixel. So if this pixel, sorry, what's going on? Yeah. If this pixel has 0, the pixel from the input is taken. Right, this is a matrix, yeah, and 1 minus each of the pixels. So it takes the input from the input pixel. If the mask is 1, it takes the generator image. This part is a regular generator.
Yeah.
It produces the entire image, but only this part is taken.
So interesting. So basically, you're generating the full image, and then you're just keeping the parts that the mask told you.
Exactly. Yeah.
And if we're looking, for example, transferring to anime, so the mask will actually be the entire image, right?
Yeah, exactly. On the anime, the focus loss
is not used.
Is 0. Yeah, exactly. Which changes the entire thing.
You know, it's cool. Like as a trick to better improve computation time, instead of generating the full image, is it possible to first generate just the mask and then use the mask and generate just the pixels that are the mask tells you to generate?
I guess it is possible. I never really thought about it. I guess I can do it.
And then you can
I
save
don't know if exactly how, but I guess it can. Maybe it will be more, efficient or something.
By the way,
produce the mask somewhere in the middle here.
How long does it take to generate an image?
You cut off. Wait, I couldn't hear your last
How long
question.
Does it take to generate an image?
To generate an image, a fraction of a second.
On a Quattro or on
almost instantly. On basically any GPU, even the 1080, to 180, yeah.
Okay.
So it will take you. I think even a laptop with the GPU can produce the image. The training is harder. Just producing an image, it's not that difficult.
Oh, I see here two questions. Marius sent first, so let's look at his. He asked, how do you think will larger number of councils impact your results? So if you can repeat that.
The larger, if the, what, if I understand you correctly, the larger the council, it's not always better because they have other time to converge to any output. So they just give up essentially and don't care about the council loss. So if they are too big, it's not, yeah.
No convergence.
Obviously, you should be as large as possible because then there is the effect of, it should be large as possible because as large as the council size is, the more better solution, if you would like to call it this, like this, like a large group of people, yeah. The wisdom of the crowds, yeah. So it will be better connected to the input domain. But if it's too big, they'll just give up.
Mm-hmm. And also Ina texted a question. I will read it out loud, but you can also see it on the chat, or maybe it will be easier for you. I'm going to read it still for anybody who's going to watch the recording. I understand.
I tried to look in the chat, but I can't see it.
So I will read it. Maybe if you can hear me, it's okay. So she says, I understand that council loss limits variability of the output so that all generators agree with each other. But I don't see where similarity with input imposed. Even conditioned of hat of D by X is not sufficient. In a way, council loss is a regularization loss that changes the shape of the optimization function to constrain having less convergence basins.
Okay, so I think I understand what she means.
We can't hear you.
So in essence, oh, sorry. Now you can hear me?
Yeah, maybe, you know what? Maybe if you can try to close your video, your
sorry,
might be your network is slow.
Sorry.
So yeah.
Yeah, sorry. Just, yeah. Okay, can you hear me now?
Yes.
Okay, so in essence, this regularization, the generators can produce, they can agree on any transformation, even if it's not connected to the input. But it's harder to agree on something random, right? The only thing that connects between all of them is the input. So it should be easier to connect based on the input, rather than just making a random transformation. Right? If they take a black man and one makes a blonde and the other makes whatever, it's harder in essence. Right? I hope I made myself clear. Yeah, it's easier if the traits are matched. It's easier for the multiple generator to coordinate on something that is common in the input, rather than just a conversion random, random output.
We'll give Ina time to respond. And there is, Marius mentioned on the chat, I would bet that the glasses removal example, especially for the imbalanced data set, improves if you use the cycle-GAN property only on the inverse mask.
Only on the inverse mask. If I use the cycle only on the inverse.
I'm also not sure.
Again, if you have a cycle loss on the inverse side, you still need to come back to glasses at the end. So I don't quite understand what you mean.
He mentioned this with regard to the imbalanced data set, I feel. That if you remove glasses, then the output is more female. Maybe about this.
Oh yes, exactly. Yeah, yeah. If you use the cycle constraint, it's more pixel wise, like taking the input and the output and do a loss between them. So the yeah.
You are really cut off, Oli. We can't hear. We lost you in the beginning of the answer. Still cut off. Still cut off. I feel like a machine. I'm talking the same sentence until he hears me. Still cut off.
We'll make it work. Maybe I'll try to reconnect maybe.
You know what we can do? I think anyway, we are running out of the time. What we can do, Ori, if it's okay, if you can write an answer for this question via text, and I will also post this on the references. And maybe what we could do is if anybody else has questions, post it on Reddit and Ori will answer. Is this okay?
Yeah, sure.
Yeah, because I think the connectivity is a bit hard to work with right now for us. Sorry about this. Sorry about this, everybody. These things, you know, they happen.
Yeah,
but
sure.
It's actually, it might be even better to have the text on Reddit, so it's more accessible even, so that's okay. I will save all the texting from now and I will post it also, so we will have all the access to all this information. If that's okay with everybody, I will want to say no concluding remarks. I'm going to turn my video so you can see me. Again, apologies about the connectivity. Sometimes these things happen. Ori, this was a very interesting talk. The tricks along the way.
Yeah, thank you.
The tricks along the way, I think it's very important to anybody practicing and really implementing neural networks themselves to take a look at these ideas and maybe come up with your own. But this is how you come up with good results. You, for example, choosing 4 members because you understand if there will be convergence to a good spot, 4 members is the best way to do it. This is thinking ahead. Good job.
Yeah, thank you.
And really interesting results also.
Thank you for the organization. I really enjoyed it. Yeah.
Thank you.
And forward for the future.
Thank you. And thank you, everybody. Again, all of this is happening because we see that people are interested and want to come and want to listen and want to ask questions and take part and participate when it's live online and when it's offline, when there's the recording and people still communicate. I am gonna share again all the links to where you can find us on Reddit, on YouTube, where this recording will be posted. The newsletter when I will update when the recording is online and where I will be updating other recordings and other events. The Discord server where there's the instant messenger chat where people communicate and ask questions and share knowledge. Only if you would want, you can also join the Discord and maybe, you know, answer questions there.
I think I'm already there, yeah.
Ah, perfect. So Ori is there, so feel free to ask the questions there. It's even more comfortable.
Yeah.
I would ask anybody who's asking.
Familiar how it works, but yeah.
Okay.
I'm not efficient on Discord, but I'll do my best.
I will ask Sil to post the questions on Reddit because it will be better for everybody in the future who wants to come to the reference. What else I have here? Yeah, I am always looking for more lectures, more talks, more interesting things to teach us and to show us. So anybody who's familiar with somebody who has something interesting and in high end to share, please let me know. Yes, Oli, again, really thank you so much. Again, you know, the connectivity issues, what can we do about these things? It's random life.
Maybe next time I'll find a better space. Now with COVID, if there wasn't COVID, I would be in the Technion where their internet is perfect. But yeah,
it's okay. So many people saying thank you. We can see on the group chat. I will send you all after. Thank you. Need to think about all of this for sure.
Yeah,
cool ideas. Again, thank you everybody for the support. I will be the last one to disconnect because when I disconnect, everybody disconnects. So just anybody feel free to, if you have something to say, say. If not, you can disconnect and I will close in the end. Okay, I'm gonna close. Bye all.
Okay, goodbye. Bye bye.